All right, so today we're going to finish up 5.1. And the only thing left in 5.1 is converting back the other way. Okay, so we've looked at how to convert from polar to rectangular. That's where you use the two formulas, x equals r cosine theta and y equals r sine theta. So the first formula gives you the x, the second formula gives you the y. Now we're going to convert the other way. So we're going to be given a rectangular coordinate. Can someone tell me the names of the two variables that we use when you have a rectangular coordinate? Yep. We have an x and a y. So for this point right here, you would be given the x value and the y value. Remember, x value is horizontal movement, so you would know how far to the right, could be left, but in this case it's right. And then you would also know how far up. It could also be down, but in this case it's up. So you'd know those two things. What are the two things that we need to figure out to write that coordinate in polar? We want to convert the x and the y into a what and a what? Yeah. An r and a theta. What does r mean? What does that stand for? How about Jacob?
Radius.
That stands for the radius. Radius of a what?
Circle.
Of a circle. So this point right here, if you're trying to figure out what it is in polar, you need to figure out how big of a circle is it on. So basically, you need to figure out this. What's the radius of the circle that it would be on? So here is your radius. From the center of the circle right to the edge. Got my radius. And the other thing I need to figure out is theta, which represents my, what does theta represent? Yep, that's an angle. So after you've moved out to the correct circle using the radius, how many degrees do you need to rotate? So it's exactly the same diagram we had yesterday. The difference is what two things in the diagram you know. Today you know the x and you know the y. And I'm going to write this down a little bit more organized in a second, but just to kind of look at it quick. How could you figure out r if you knew x and you knew y? Oh, James, how would you get r?
The Pythagorean theorem?
Yeah, we can use Pythagorean theorem because you're going to know two sides of the triangle. So that's not something we used yesterday because we didn't have to solve for r. We already knew it. But today we're going to have to solve for r. So we can use x squared plus y squared equals r squared. Okay, and again, I'm going to write this down nice and neat in a minute. But I'm just putting it up there for a second. So we've got that. And now let's look at solving for tangent. Autumn, what's the name of the side that we've called x and it's right next to my angle? So do you remember that, like, let's start with r. What side is that? Because it's across from a 90. That's hypotenuse, yep. And how about, let's try the other one then. What about the side that's furthest away from my angle? Yeah, could you say it again?
Opposite?
Yep, that's opposite. Now, do you remember the side, the name of the one that's closest to the angle? Adjacent, good. So in this problem, you know the opposite side, that'll be the y value of your coordinate, and you know the adjacent side, that's the x value. What trig function has opposite and adjacent in it? Done?
Tangent.
Tangent. And again, I'm going to write this down neater on the next page. I'm just kind of showing you where it comes from right now. but it's going to be tangent of your angle equals opposite over adjacent. Now, that's great. I got a formula with opposite and adjacent, but I want to have theta. I don't want to have tan theta. So how would I get rid of the tangent on the left-hand side? So it just says theta equals. Yeah, Olivia?
Inverse tangent.
Yeah, we're going to have to take the inverse tangent. Take the inverse tangent of what's on the left. That's going to cancel out. Take inverse tangent of what's on the right. And there is a formula that is going to give you theta. It's going to give you inverse tangent of y over x. Now, the only problem with that formula is if you remember when we studied inverse trig, inverse tangent always gives you an answer between negative 90 and positive 90. So let's think about that on this circle. Where's 90 degrees on that circle? Well, Colby,
What?
where's 90 degrees?
Would it be the y-axis?
Can you be more specific?
Would be at the top of the circle, right?
At the top, right on the positive part of the y-axis. So here's 90. All right? Inverse tangent is always going to give us an answer between negative 90 and 90. Well, there's the part between negative 90 and 0. Or, I'm sorry, between 90 and 0. Where's negative 90? Yeah,
Straight down.
straight down. So if we look at that part, that would bring us, let's use the color, down to here. So inverse tangent will always give us an answer in that section. The problem is that only covers half the circle. What if we had a coordinate in quadrants 2 and 3? Inverse tangent by itself would never give you an answer in those quadrants. So when we have a coordinate that ends up in quadrants 2 or 3, we're going to have to make a small adjustment to that formula to make it work in those quadrants. But it would work perfectly fine in quadrants 1 and 4. Okay, I'll show you in a second what the adjustment is to make it work in quadrants 2 and 3. So, when we're converting from rectangular to polar, because that last formula I showed you is going to change a little bit, if you're in quadrants 2 or 3, that's the first thing you need to know. If you can figure out what quadrant you're in without graphing, that's fine. But the point to that first step is figure out what quadrant you are in somehow. So that's the first step. Now you have to find the angle and you have to find the radius. It doesn't matter which one you do first because they're totally separate. Okay, I'm going to do the angle first. That's a little more complicated because the formula you use depends on the quadrant you're in. If you're in quadrants 1 or 4, you're going to use the exact formula that I just put up on the other page. Inverse tangent of y over x. And that formula works perfectly fine in those quadrants. If you are in quadrants 2 or 3, okay, that's the left half of the circle where inverse tangent will not ever give you an answer. You have to take that formula and you have to add pi to it if you're doing it in radians. If you're doing it in degrees, you would add 180. Okay, so you only have to add 180 if your point is in quadrants 2 or 3. Okay, how can you quickly tell if your point is in quadrants 2 or 3? Well, in quadrant 2, the x value is negative and the y value is positive. In quadrant 3, the x value is negative and the y value is negative. So basically, anytime you're trying to convert a point that has a negative x value, you are going to be in quadrants 2 or 3. So the top formula covers what to do if you're in quadrants 1 and 4. The bottom formula covers 2 and 3, but that's not everywhere you could be. Where else could your angle land besides in quadrants 1, 2, 3, or 4? Yep. Well, it's going to be on a, pretend like we have a circle here. It's going to land on the edge of that circle somewhere. Yep.
What are their options?
It could land on an axis. So think about if you were on an axis. And let's say you were trying to find the angle for this point. I don't know what the y value is at that point. It's up. I don't know how many it's up. Maybe it's up 4, maybe it's up 5. I don't know. But I do know the x value. What's the x value of a point that's on the y-axis? Yep. 0. X value is 0. What would happen if you try to plug in an x value of 0 into either one of those formulas that has a box around it? What would you end up doing? Yeah? Why? You can't ever divide by 0. So these formulas work exactly when I told you they work. They work in a quadrant, not on an axis. Okay. If you're on an axis, that's a special case. You just have to memorize the 4 answers you could get. 0, 90, 180, and down is 270. You have to know those 4. Okay? But other than those 4, those formulas will work all of the time. So any questions why you can't use those formulas if you're on an axis? Because at least on the vertical axis, x would be 0, and it would cause you to divide by 0, which you can't do. So now that covers every possibility you could have for an angle. In a quadrant, on an axis. So once we have the angle, last thing we usually finish up with is the radius, and for that we just use Pythagorean theorem. That's the same formula no matter what quadrant you're in. Doesn't matter. Right, we could end up again here with a square root in the final answer. And remember our rules for square roots. Don't leave them in the denominator. That shouldn't happen because we're not really going to deal with too many fractions. But also you have to simplify any root that you can. Okay, so like square root of 12 would be 2 square roots of 3. Okay, that kind of idea. Okay. So let's try a couple examples converting from rectangular to polar. So there's a rectangular coordinate. We know that it's rectangular because it says convert to polar. So it's not polar. They want us to make it polar. So there's my x, there's my y. Okay, Ben, what quadrant is that point going to be in?
4.
Yeah, it's going to be right 2, down 2. So we're not looking for an exact sketch, somewhere right around there. But the point is, it's in quadrant 4. Jade, what's my formula to find theta in quadrant 4? Theta is your angle, yes. Do you have it written? You don't have to memorize it, but do you have it written down? No? Can anybody help her out? What is the formula to find the angle in quadrant 4? Lacey?
Would it be theta equals inverse tangent y over x?
Inverse tangent y over x. Am I supposed to add 180? You think, Cassidy?
No.
No, not in quadrant 4. Nope. Quadrant 4, you just do inverse tangent of y over x. Okay, so inverse tangent of, yes,
Because x and y are both 2, like one's negative, but they both have the same number, would you be able to say that it's just a 45? Because
yeah.
so if like on a test you just did that without doing the math, would that be fine?
Sure. So I would look at that too, and I know that that's going to end up being some type of 45-degree angle because the x and the y values are opposites. So it gets a little trickier when you have an x and a y value that are like a 4, like different numbers. Then you really have to go through. But yeah, anytime that these two numbers are the same or opposites, it is always some type of 45 because you've gone over and up the same amount, or over and down. Right? But in case you don't know that, let's just go through it. So that's -2, that's +2, and that's going to be the inverse tangent of -1. Right, so I'm going to do this in degrees. Let's do second tangent. And again, if you want to type it in as -2 divided by 2, you can, but I know -2 divided by 2 is -1. And I get an answer of -45 degrees. Now we'll talk about that in a minute. There are other ways you can write the angle besides as a negative. Yesterday I showed you guys 4 different ways you can write polar coordinates. I'm not going to go through all 4. Maybe we'll do a couple. But let's stop with the angle for now. Okay, so we got that. Now I need to find my radius. Raymond, how do I get my radius? And what formula is that really?
R equals
Yep.
x squared.
R squared equals x squared plus y squared. And that's really just the what with different letters? Because I want to make it a point, this isn't something new. This is a formula you've used in geometry a lot. You just normally don't use these letters, but it's the same formula. Yeah. Yeah, it's just the Pythagorean theorem, right? Here's your point. Your goal is to figure out how far that point is from the origin. Well, this side's 2, and that side, I mean, it's -2, but you're going to square it, so it's going to become 4 anyway. You're just finding out the length of the hypotenuse in a triangle. All right? So r squared equals 2 squared. And again, if you want to put the negative with the y, you can, but it doesn't make a difference when you're squaring it. All right, so when we do that out, how about, Eva, what's 2 squared?
4.
And -2 squared?
-4. Oh wait, no, 4.
4, yeah? Because that means -2 times -2. So we get r squared equals 8. And Mateo, what would I do on each side to get rid of this exponent of 2?
You would divide.
You'd use division if you had multiplication to get rid of. We don't have any multiplication like this. That would be a division problem. So what? Can you just read that equation to me?
So that was. I forget what the R is called. Sorry.
You can just say r. That's
My
fine.
R. Okay. So R squared equals 8.
R what?
Oh wait.
I just want you to say it again.
R squared.
Squared. So we have to get rid of squared. That's a something we have something else that's the opposite of squared.
Not squared. I don't know.
We want that to be not squared, and to get it to be not squared, we have to take the Yeah, Chad? We have to take the square root. So we take the square root of both sides, we get square root of 8. And remember, you can break that down into square root 4 times square root of 2, which is 2 square roots of 2. So if they want an exact answer for the radius and they don't want a decimal, that's what they'd be looking for. 2 square roots of 2. All right, let's just write our coordinate now. So we've got r and we've got theta. So 2 square roots of 2, negative 45 degrees. So doing it that way, you're going to the right, and then you're going clockwise. So it's like you're going right, and then rotating clockwise. What could you do to this angle to make it positive? Let's say instead of going clockwise, you're going to go all the way around counterclockwise. You want to remember how do we change that negative angle to a positive? Yeah,
Add 180.
adding 180 would only bring us partway around. It would bring us to a different spot.
Yeah,
We have to add 360, so it brings us all the way back to the same spot. And what do you get if you add 360 to negative 45?
Is it 250?
So think of it as like 360 minus 45. Yep, 315. So there's two different ways you could write this answer. Positive radius, negative angle. Positive radius, positive angle. Okay, we've gone through all the 4 ways you can do it yesterday. You could do a negative radius with a negative angle. You could do a negative radius with a positive angle. All those answers would be correct. It would just be a matter if it's multiple choice. Let's say you got this as an answer, but maybe all my answers have positive, positive instead. Okay. There will only be one correct answer, though, per problem. Questions on that one? All right, so that's one where we did it as an exact. Let's do one where we're going to round it to a decimal. Okay, so we'll round everything off here to 2 decimal places. All right, so Aiden, what quadrant am I in this time?
Quadrant 3.
Yep, I'm in quadrant 3. Left and down. Okay, so I'm in the lower left quadrant. What's my formula for theta if I am in quadrant 3? Yep.
You have to do pi, and then the inverse tangent, and then y over x.
Okay, and one other thing we need in there.
The plus or minus. Oh wait, plus. Sorry.
Plus. Now, he said pi, which is fine, but that means we're doing this problem in radians. That doesn't affect how you find the radius with Pythagorean theorem. That's just the distance. That's different. But because he chose pi, I need to make sure my calculator is in radians. What could he have picked instead of pi if we wanted to do this in degrees? Olivia? We could have put a 180 there. Okay, all it does is change the mode button that I press on my calculator. That's it. All right, so theta equals pi plus inverse tangent of, now y and x are both negative, so they're going to cancel out. -5 over -4. So when I type it in, I'm just going to type in 5/4. Okay, I need to make sure I'm in radians because we said pi. And that's the only thing that changes my mode here. Okay? So I've got pi plus inverse tangent of 5/4. So that's about 4.04 radians. Okay, that's my angle. Okay, so we got that. Now we have to figure out my radius. And that has no effect on what mode you use because that's Pythagorean theorem. So r squared let's see, x squared plus y squared. All right, so negative 4 squared, that's going to be 16. Negative 5 squared, 25. What's 16 plus 25? James? 41. So r is the square root of 41, but I did say this time we were going to round everything off. So let's type that in and just practice doing it out. So the radius is about 6.40. All right, so my final answer is r. That's the distance I'm going to move out from the origin, and the angle, 4.04 radians. Questions on that one? All right, so that's good that he picked radians because we got to do a little bit of everything. We did one problem in degrees. We did one problem in radians. We did one problem where we left the answer exact. And then we did one problem where we rounded it off. So we did a little bit of everything. And that's the end of 5.1 part 2. All right. So let's take a look at this before we look at A4. So A4 gets into what we call complex numbers and imaginary numbers. But a lot of people don't understand where those fit in or kind of why they're needed. We're not going to really look at applications of where they're needed. That gets pretty advanced, but I will try to show you why they're needed. So the simplest kind of numbers you can have, we're going to start by putting them in the innermost box, and we're going to work our way out to more complicated numbers. They are counting numbers. Counting numbers start with 1, and they don't include any negatives, fractions, or decimals. Like 1, 2, 3, 4, 5, 6, like counting numbers. And if all you had to do all day long was just count things, you would never need any other kind of number. Right? When you're counting things, you never have, like if I'm counting how many pens I have in my hand, I never would have half a pen. If I have half a pen, it's broken, right? But generally, when you count things, it's a number that's not a decimal. How many of them do you have? 26. So the problem can come in when we start to do arithmetic. Addition wouldn't be a problem. Ben, can you give me a counting number? 2. And James, can you give me another counting number?
5.
5? No matter what two counting numbers they said, it wouldn't have mattered. I was going to add them together. And the answer is always going to be a counting number. If you take a counting number and you add another counting number, you will always get another counting number. But let's look at what happens with subtraction. And I'm not even going to do it with two different numbers. I'm just going to use the same numbers. 2 minus 2. That's a problem that could come up in everyday life. It's not a rocket scientist level problem here. 2 minus 2. Is 2 minus 2 a counting number? You think, Cassidy?
No,
No? Why? What do counting numbers start with?
I don't know. What?
What do counting numbers start with?
A positive?
Exactly what positive number?
A counting number?
Yeah, what number do counting numbers start with?
I don't understand.
1.
1. Like if you're counting, they start with the number 1. What's 2 minus 2?
0.
What?
0.
What's that?
Less than 1.
I don't understand. I only understand counting numbers. So you just said something that's new. I have no idea what you're talking about. It's 0? Where do you get that from? So it's like this new thing, right? It doesn't seem new to us, but at one point, you can look it up, 0 didn't always exist. It was invented at one point because people realized they needed a way to represent the idea of having nothing. rather than just always having something. And 0 represents the idea of nothing. You don't have anything. If you were counting, 0 wouldn't make sense because you wouldn't be counting if you had 0 things. Like if you asked me to count, how many, I don't know, how many oil filters I have in this room, well, I wouldn't be doing that because I don't have any. So I don't need a way to represent 0. I just wouldn't even count them. They don't exist in this room. But 0 represents the idea of having nothing, and that's called whole numbers. So now, if you have a problem like this, you can actually write down what the answer is. We invented a number to represent the idea of nothing. But we can still have other problems with subtraction. Right, let's go back to this first one we had, and instead of adding them, let's subtract them. Okay. All whole numbers do for you is give you 0. That's it. They don't give you fractions, they don't give you negatives, they don't give you decimals. All they do is give you the number 0 as an extra number besides counting numbers. Is 2 minus 5 going to be a whole number? You think, Mateo?
No.
No. Why not?
Because it doesn't start with 1.
Okay, yeah, this number is even before 0. It's the idea of forget even having nothing. Now you have less than nothing. All right. So when we're dealing with subtraction, we need a way to represent the idea of less than nothing. Could you have less than nothing in real life? Absolutely. Like if you borrow money from the bank, that's the idea of being in debt. So not only did you not have enough money to buy what you wanted to buy, you had to borrow it from someone else, and now you have to pay them back. So now you have money you owe somebody. That's like negative, right? You're in debt. And those kind of numbers we call integers. So integers give us a way to represent the idea of less than nothing. Still pretty practical. I would say you definitely deal with negative numbers in real life. Being in debt, or if you have a budget, when you have a company and it comes out that you spent more money than you made, well, you lost money. So it's like your money is negative that month, right? Because you spent more money to make your product than you did selling it, right? So that would definitely be an integer. But while we're talking about money, when we deal with money, our amounts of money always nice numbers, like 6, 3, 2, 5, 1, negative 8. No. We can have parts of those numbers, right? Or when we divide, we can also have parts of numbers. Well, integers don't let you have parts of numbers, right? If you had, let's say, 4, and you want to divide that by 3, well, that's impossible if I deal with integers. That's like me having 4 $1 bills in my hand, and I want to give them to 3 people equally. I can't. The only way I can do that is if I start breaking things into pieces. And instead of giving everybody maybe a whole dollar, they get a fraction of a dollar. Right? And maybe they get 67 cents or something like that. Okay? But those are parts and pieces. And those are called rational numbers. So we invent numbers that allow you to represent parts of something. Again, I still think rational numbers are pretty practical. Like if you're cooking, maybe you don't need 2 cups of flour, but you don't need 3. You need something in the middle. Well, you need a way to represent what's in the middle between 2 and 3. So you have 2 ways to do it. You can use a decimal, like 2.6. Or you can use a fraction, like 2 1/2. Okay? 2 1/2 cups of flour. Okay? For most everyday purposes, rational numbers are about as complicated as people get, okay, for like everyday kind of stuff. But in math, we still have other operations that we could have a problem. It wouldn't necessarily be adding, subtracting, multiplying, or dividing. But where we could run into a problem would be with a number like this, or a number like this. Rational numbers allow you to represent things as fractions, pieces. There's another type of number to represent things that are not rational, things that you can't write as a fraction. Right? And we dealt with numbers like this in the last section. We had to find the radius of a circle. It's square root of 2. That's a number that can never be written as a fraction. So people like to have labels for things, so they give a name to that. Does anybody know what you call a number that cannot be written as a fraction? Rational is a number that can. Yep?
Irrational.
Irrational. So irrational numbers are numbers that you can't write as a fraction. Now, you might say, well, what about maybe someday we can write square root of 2 as a fraction? We just don't know how to do it yet? No. I could prove that it can never be done. Like, no matter what. You will never be able to write the square root of 2 as a fraction. It is absolutely impossible. Right? Pi, we think it's impossible. Not sure we have a proof on that one yet. But at least we know if you write out pi for a very long time, there is no pattern to it. And by a very long time, I mean hundreds of millions of digits. So chances are it cannot be written as a fraction. But square root of 2, that's a definite. Can't do it. And when you take all the numbers that you can and can't write as fractions, that's what you study in Algebra 1. And those are called your real numbers. Okay, real numbers. But there is something I could do on the calculator. I'm going to type in square root of -4. I want to see what the calculator tells me. So when I try to do this, that means I'm trying to find, I'm trying to find two numbers I can multiply together to give me -4. But they have to be the same. Can anybody think of two numbers that are the same? Because that's what square root means. Multiply two numbers together to get what's under the root. Two numbers that are the same that multiply to give me -4. Why can't you do that? You just need two numbers that are the same and multiply to give me -4. Why is that so hard? Yep.
In order to get a negative number, you have to multiply a negative by a positive, so they won't be the same number.
Right. So if you're thinking this way, then yes, you're correct. The only way to multiply two things together and get a negative is if they're different. One has to be negative, one has to be positive. So what if in math, though, we come across something like this and we have to write down an answer? So what do we just say? Do we do the same thing here? Like if you don't understand what nothing means because you don't know the number 0, do you just say 2 minus 2 is, I don't know, error? You don't know how to do it? Well, just because you don't know about the number 0 or you don't know about negatives or you don't know about fractions doesn't mean you can't write the answer. Like somebody in first grade might look at 4 divided by 3 and say, you can't do that because they don't understand fractions yet. But we understand fractions and we know you can do that. Well, it's the same idea here. If you don't understand what the answer is, then you would say, well, you can't do that. But that's like saying you can't do 2 minus 2. You can. You just don't know how. So when we deal with square root of -4 and I type it in on the calculator, even the calculator says, error, you can't do it. But that's because the calculator is trying to give me a real answer. Well, you can't do it that way. If you want to give an answer to a problem like that, you have to go beyond real numbers. And we have to look at a different kind of number, and that number is called imaginary. So all we're basically doing when we answer that is we're inventing something to represent an answer to that problem. Just like we invented the number 0, just like we invented this little thingy to represent less than 0, we invent this thingy to represent an answer to a problem like that. It involves an I. And if you see it on the calculator, they put that I in there. All right. So these are called imaginary. Applications of imaginaries, way beyond what we do, right? Even that's more like a college level or even like engineering. If anyone knows about engineering, you might know some examples where you use imaginaries, but they're not something that the average person uses in everyday life, which is why we're not going to look at applications, okay? We're not really going to get into word problems with imaginaries. Those would be pretty tough. So this whole thing is a diagram of the complex number system. And that's where I'm going to start with section A4. Complex numbers have two parts to them. They have a real part and they have an imaginary part. So every number you've ever studied is a complex number. Every number that you've ever studied in high school. Is there something beyond that? Like, is there some other kind of math problem where we would have to invent another thing to write the answer to it? That I don't really know. But I do know complex numbers are pretty much the limit of what I've studied. Doesn't mean there isn't more that I don't understand. Okay. So we usually write complex numbers in what are called standard form. Standard form of a complex number puts the real part of the number first and the imaginary part of the number second. So when I point to these different things here, A would be called the real part. B is the imaginary part. The I is just there to tell you what's in front of it is imaginary. That's how you know it's imaginary. You put this I. Okay. And an example would be something like that. 2 plus 3i. That's a complex number that has a real part of 2 and an imaginary part of 3. It wouldn't be wrong if you wrote 3i plus 2, but that's not normally how we do it. That's not standard form. Okay, on the test, in fact, all of the answers for complex numbers are going to ask you to put them in standard form. Any questions on what the real part and imaginary part is there? Okay. Now, sometimes you could have a number that doesn't have a real part. Think of it like this. 0 plus 4i. Well, if the real part is 0, or anytime something is 0, we normally don't write 0. We just write 4i. If a number doesn't have a real part, because it's 0, we call that a pure imaginary number. So there's a couple more examples of pure imaginary numbers. 4i. The real part here, if I asked you, is 0. The imaginary part is 4. The next one is negative 2i. If I asked you what the real part is there, you'd say 0. Imaginary part, negative 2. Okay, any questions on that? Now, earlier I said every number that you've ever studied in like a high school math class is a complex number. You might say, well, I've looked at lots of numbers that don't have I in them. Well, that's fine. Complex numbers don't have to have I. This is a complex number, 5. That's a complex, I don't want to write it under pure imaginary though, because it's not imaginary. 5 is a complex number. It has a real part. If something has a real part or an imaginary part, it's complex. Think of the imaginary part like this. There is no imaginary part. When the imaginary part is 0, we normally don't write it. We would just write 5. All right, so what does it mean for two complex numbers to be equal? So let's say those are our complex numbers. The first number has a real part of A, and the second number has a real part of C. The first one has an imaginary part of B, and the second one has an imaginary part of D. In order for these complex numbers to be equal, then the real part of the first number has to match the real part of the second number, but that's not enough. The real parts have to match, and the imaginary parts have to match. Normally when you ask if two numbers are equal, there's only one thing you need to check. You just have a number, and you just check it with the other number. With a complex number that has a real and imaginary part, you need to check two things. Do the real parts match? Okay. Do the imaginary parts match? Okay. If they do, then they are considered the same number. I know it's pretty simple, but that's what it means for two complex numbers to be the same. 3 plus 8i and 3 plus 8i. Those are the same complex number. If I did something like this, you say, well, are those the same? Because the 3's are the same. No, they're not the same. Are they partially the same? Well, the real parts are, but the imaginary parts are not. So this is all or nothing. They either both have to be the same, and if that's not true, then they're not equal. Okay. Question on that idea. All right. So the last two things we're going to look at is how do you add complex numbers together and how do you subtract them. Well, adding and subtracting is pretty straightforward. Think of it as combining like terms. If you want to add two complex numbers together, you can add the real part of the first one to the real part of the second one. Those can be combined. And you can add the imaginary part to the imaginary part. And that's it. You can't combine real and imaginary parts together. So if you have this, you can't say that that's like 9 something. You can't add the 3 and the 6 there. Because the 3 is real and the 6 is imaginary. Okay, but you can add real parts to real parts and imaginary to imaginary. So let's look at this one. So this one says 3 plus 8i, or I'm sorry, yeah, 3 plus 8i plus 8 plus 2i. And we're going to add those together. Now I may not write in the directions add. All I have to do is just put the symbol plus between them, and you need to know that that means to add. Right, so Angie, what's my what's the real part of the first number in parentheses?
3.
3. And what's the real part of the second number?
8.
And what do you get if you combine the two real parts you just told me?
11.
11. So that is part of the answer. It's going to be 11. And the imaginary part of the first one is 8. Imaginary part of the second one is 2. What do we get if we add 8i plus 2i?
11 plus 10i.
11 plus 10i, yeah. I try to make my ones not look like i's. That's going to be a mess if you get confused on the test and you're trying to look through quick and you're like, wait, is that a 1 or an I? Try to make them look different. So that's 11 plus 10i. All right, let's try that one. 4 minus 2i plus 3 minus 8i. So, Don, when I add those together, what's going to be my real part?
7.
7. Okay. And Raymond, when I add those up, what's going to be my imaginary part? Okay, what's my imaginary part in the first parentheses? Just imaginary. We're done. The 4 is all done. 2i. Negative 2i. And what about in the second parentheses?
Negative 8.
Yep. And now when you add those together, what do you get? Say it again. No, not 10. You said negative 2 and negative 8, right?
Yeah.
I like that. If I owe you $2 and I owe you 8 more, you're going to pay me 10. I like it. So what should it be?
Negative 10.
Negative 10. Yeah. So it shouldn't be a positive 10. It should be a negative 10. Negative 10i. Again, I should make my 1 look. Okay, questions on that? Now subtracting, pretty much the same thing, except think of this subtraction sign as being distributed. You're going to subtract C from A, and then you're going to subtract D from B. Okay, you're subtracting both of the numbers in the second parenthesis from the numbers in the first. And that's the calculation that you're pretty much going to do in your head when you're trying to figure it out. Subtract the reals, subtract the imaginaries, just don't forget to put your I at the end so we know it's imaginary. Alright, so Jacob, when I subtract those two numbers, what would be my real part?
4 and 3.
And when you subtract them? 1. That's going to give me 1. And Lacey, what about my imaginary part?
12i and 4i.
Yep, and the final answer?
Wouldn't it be, you're subtracting them still, right? Or would you add them because the pluses in front of them?
Well, you need to do whatever, because that's how it'll be on the test. I wouldn't be able to answer that on the test. I can answer it now. But you're subtracting, right? You're just subtracting a positive number.
Okay, so it'd be 8.
It'd be 8i. Yep. So it's just 12i minus a positive 4i. Okay, so that is subtracting. Right, and let's try that one. 3 minus 5i minus 8 minus 6i. Anyone think they can give me just the final answer? James?
Would it be negative 5i plus I?
So the real part is gone?
Wait,
The real part can be
did I say
gone.
negative?
You said negative 5i.
Oh, I meant just negative 5.
Okay, yeah, negative 5. And what else?
1i, or plus 1i.
Plus 1i. That's negative 5i minus turns into a plus. So negative 5i plus 6i. You can put 1i, or you can just put I, that's the same thing. Any question on that? So we've been writing this I everywhere. Right? We put I's in all these different answers. I keep talking about I. Well, I never really told you what I is. Because you didn't really need to know what I is to do all that stuff we just did. How come? Well, you just did it. You asked you guys all these questions and you figured out all the answers without me even telling you this. But this is what was invented to represent the square root of a negative number. Okay. Now, why didn't they use this symbol? I don't know. I guess you could have, but that's a more complicated symbol. They chose to use the letter I. Just the letter they used to represent the square root of -1 because there was nothing to represent the answer to that problem before they invented that. Okay. So I equals the square root of -1. And again, if you ask me why, I would say because. It's like asking me why do parallel lines not cross? Because they don't. It's just the way it is. It's one of the basic things like in geometry that you got to start with something, and that's a definition, or it's a postulate. Parallel lines never cross. In Euclidean geometry, it's just something they say. Same thing here. This is something we say, you cannot prove why it's true. It was invented. That's what everybody agrees on. Why are stop signs red? I can't prove why. I don't know. It's what everybody decided to agree on. Red's a nice color. I don't know. All right. So I equals the square root of -1. So as long as we all agree on that, then from there we could figure out other things like this. I times I would be that times that. You're multiplying two things that are the same. So it really means this. The square root of -1 times the square root of -1. So what would that be? If you did the square root of -1 squared. Yep.
-1.
You'd get -1. Anytime you square and square root, they cancel out. And you're left with whatever you started with under the root symbol. So the idea that you could take an imaginary number and multiply it by itself and end up with something all of a sudden that's not imaginary and the I is just gone, we're going to use that idea tomorrow in order to get rid of I's where we don't want them. Okay, we'll pick up with that tomorrow. So the first part of the homework on 308, that is on the converting between the rectangular and polar. And the second part of the homework, page 560, that's on adding and subtracting complex numbers. Okay, so we'll look at those tomorrow. And tomorrow will be the last day of new material for the week. And then remember, we have Thursday off, and Friday will be technically our second test for term 2.